Okay, well, today we'll be talking about an introduction to HMMs, or what are called hidden Markov models for time series data, like we're using in this class. I've broken the lecture up into 4 parts. We'll first kind of just gently talk about what HMMs actually are. We'll discuss a brief overview of some theory and the notation that we use to describe these models. And then we'll jump right into a couple examples, both a univariate example of fitting HMMs in R using the Detmix S4 package, and then again we'll jump into some multivariate examples with some of the same software tools. There's a bunch of materials out there for brushing up on these applications and the estimation for HMMs. In particular, I think there's a couple really good books out there. The Zucchini et al. First and second editions have been really helpful, I think, for me understanding what HMMs actually are. And then there's a few different packages out there on CRAN for fitting these types of models. And so MSM is one, Detmix S4 is another, and we'll be using both for this lecture. So to date, we've discussed a couple different flavors of state space models. We've talked about kind of the classic univariate state space model where we have a process model and then that describes kind of a state of nature that we don't actually see or observe. And then on top of that, we have layered this data or observation model, which is just generally interpreted as kind of our measurement error or observation error. And that introduces an additional layer of noise that kind of separates out the signal that we really are interested in from that noise. This can be done again in a univariate or a multivariate setting, and we often assume that both the process deviations in the true underlying state of nature and the observation deviations representing that jitter or that additional noise are both normally distributed, but you could have any number of other distributions for these two types of models. For the notation for these models, this should be pretty familiar at this point. We have, the basic random walk model is probably the simplest of the process models. You could include AR or moving average components on top of this, or additional covariates. And then in addition, we have this observation model. And again, we can have any number of other ways to make this more complicated using additional covariates or time-varying parameters, time-varying variances in each of these cases could be an additional possibility. But the simplest case, we assume that the deviations for the x sub t's, which represent our underlying hidden state of nature, and the y sub t's, representing our observed data, are both normally distributed. So, as I said before, one of the ways to make these a little bit more complicated is to add an AR parameter or autoregressive parameter, which, a random walk model is just going to drift away from the mean. So it's not going to necessarily be reverting back to the same mean value. When we add this AR component, then that property no longer is the case. And so the AR component will basically allow that process to kind of revert back to a common mean. But for some data sets, this might not always work. For example, especially in the case where we're interested in systems where we have different regimes. And so this is pretty popular, for example, in the engineering literature. We could also think about in kind of a ecology or fisheries setting where we are kind of alternating between multiple regimes with, for example, different fish stocks are highly or experience high productivity or low productivity depending on whether the environmental regime is in a warm or cool period. There's been a number of different cases or applications of this. I think there's the most common way to approach this is kind of a two different alternative stable state regimes where we have maybe cool and warm periods, like in Tessa Francis's paper here. But we might also include more regimes. So we could have a 3 or 4 regime system. And this is more often the case, I think, when we're dealing with thinking about, say, movement data. So one of the big applications that's up and coming for HMMs in ecology has been fitting HMMs to animal tracking data, where we have the track of an animal in latitude, longitude space, so that's kind of a two-dimensional vector. We might have covariates in addition, representing some environmental conditions. But ultimately, what we're interested in is identifying different behavioral states of those animals just based on the tagging data alone, or the tagging data and the environmental covariates. And what we get is we can start fitting models that have 3 or 4 different behavioral states representing animals that are, say, traveling or foraging, or diving could be a third state, for example. So I think there's a number of different possibilities to think about of classifying these regimes in this HMM framework. Historically, there's been a lot of different ways for detecting regimes without the use of hidden Markov models. One of the more common has been what are known as this STARS algorithm. And so this is kind of a sequential t-test approach where you divide the data and you do this sequential t-test to detect think about it like a running average. So or a moving window running average. But you're looking for significant differences in the mean as you run this through the time series. So that's one approach. You could also do what we've done in the class before, which is kind of this brute force model selection approach, where if you had a time series of 30 years, for example, we could iterate through every time step of that time series and then iteratively test with either likelihood ratio tests or AIC or whatever your favorite model selection tool is, and look at kind of the data support for each of those breakpoints. And that's kind of what we've done, thinking about some of the Nile River data and thinking about these change points in the mean with respect to regression or time series, where we include that your covariate there is going to be a vector of zeros, for example, up to the change point, and then a 1 after. It would be kind of the simplest way that we could go about including that covariate information in that breakpoint and doing a formal statistical test. So to illustrate this, what I've done here is just simulate some basic data. If you want to see the code for this, this is all included in on our GitHub site. And basically, we have a 2-regime system here, and we're going to alternate between kind of these two different states. We have the y-axis might represent temperature, for example, and then we are kind of alternating initially in this cool state. Then we alternate to the higher state and then back down to the lower one. And then it just kind of iteratively jumps back and forth like that. I think the probability of transitioning is something like 10% at each time step. And then the underlying state has a mean, but there's jitter around that. So that's an important part that will come up in a second. So we could take this data and we could kind of fit. I mean, the easiest way to go about it would be, we've used Mars in kind of a univariate time series setting, and we've gotten very familiar with fitting different state space models to this data, and we could use the Mars package to fit this data, and the fits are actually quite good. So this represents, the blue line here represents the estimated state of nature using Mars in a kind of a univariate state space setting, where we have an estimated latent process that's assumed to be just a random walk, and then on top of that we have a observation or data model, again that's just assumed to be normally distributed. And the blue line characterizes the latent state fairly well. I think where this might not be a good choice would be that if you were specifically interested in classifying each of your data points into one of these 2 regimes, or you were interested in specifically what was going on around these transitions, so the time points right where these transitions are occurring, the Mars type, this univariate state space model, will tend to smooth this process out a little bit more compared to an HMM, which is going to have more of a discrete break between state 2 and state 1, for example. So just to kind of recap what I just said, what the univariate state space application is kind of limiting, or what it's lacking here, is we can't estimate from the output of that model what's the probability of transitioning between state 1 and state 2. We can't also estimate things like, how long might each of these regimes be expected to last? If we're in a cool regime or in state 1 now, how long is that likely to continue? We can't also do anything about forecasting what kinds of regimes might we expect in the future, especially under different levels of covariates, for example. There's lots of applications of these types of models in other fields, including speech recognition, bioinformatics, animal movement models, as I said, modeling environmental data like rain, where we have maybe really dry spells characterized by droughts, and then periods of intense rainfall, or things like finance, where we are kind of alternating between different states, essentially different levels of volatility, or kind of bull and bear markets, for example. Okay, so that was the overview. Now I thought I would kind of talk about some of the theory behind HMMs. So like all of the other state-based models that we're working with in this class, the underlying process behind an HMM is that it's this Markov process, which just means where we are now is just a function of where we were the time step before. Time in HMMs can be discrete or continuous, but for the sake of this class, we'll be really focusing on the discrete case, which is analogous to all of the other types of state space models that we've dealt with in this class so far. And what's important here is that, as we're kind of iterating through our time series, the value of the process or the state at time t, x sub t, doesn't depend at all on future values. It only depends on what happened in the past, especially what happened the time step before. So we can take our time series and just write it down as this vector, where x is indexed from 1 to capital T, where t is the length of the time series. So one of the key features of HMMs that make these models different from kind of the conventional state space models or multivariate models like DFA or DLMs that we've used in this class are that we have to characterize or estimate the probability of transitioning between different underlying states. So these states are discrete, and so we can write the probability of being in state J at the next time step, given that we're in state I now at x sub t, is this gamma ij. What's complicated is that all of these probabilities can then be summarized in what's known as a transition matrix. And so if you've done any work with Leslie type age-structured population models, for example, you should be familiar with what a transition matrix is. What this matrix just represents then is for a 3-state system, we have to have a 3x3 transition matrix representing the probability of transitioning from state, essentially the first element is the probability of remaining in state 1, given that we're already in state 1. The probability of transitioning, again, from state 1 to 2, etc. And all of these elements might be estimated. They could also be fixed a priori, so we could know what some of these values were explicitly. We could also zero out any of these elements. So they all have to be positive between 0 and 1. And then, if we're in state 1 now, for example, the probability of transitioning to all of the other states and remaining in state 1 have to sum to 1. So there's this constraint of dealing with compositions where, given where we are now, the probability of all the other future states has to sum to 1. Okay, so our matrix then is the matrix of what are the one-step transitions. Given this matrix, we can then summarize what the probabilities are k-steps in the future using this k-step transition matrix by just exponentiating our original matrix of transition probabilities. And from this, then we can also calculate what's known as the stationary distribution of the Markov process. So there's two basic flavors of these transition matrix. What are known as homogeneous or stationary transition matrices. And so what this means is that the transition matrices are fixed. They don't depend on t, the time step, or the non-homogeneous case where the transition probabilities themselves might be time varying. So for the purposes of this class, we'll be really focusing on the homogeneous case where these things are fixed in time, but we might allow for covariates to affect covariates that could be potentially even time varying affect what the transition probabilities are. So covariates in HMM might enter the model in one of two different ways that we'll explore. The first is the effect on the mean, and so that's pretty straightforward, and we'll go through some examples. The second is effects on the transition matrix elements, or these transition probabilities. So for effects on those probabilities, we have to remember that those transition elements are constrained to be between 0 and 1, and again, they have to sum to 1. So if we're going to include covariates here, we need to do some kind of transformation so that we preserve those properties and also include for covariates. And so I think one of the most common approaches here is dealing with multivariate logistic or logit regression, which can be used to relate those covariates to elements of the transition probabilities in this transform space. And when we do this, it's just good to keep in mind that, like with logistic regression, where we're dealing with including, say, a factor variable, we have to take one of those factor variables and use that as the reference or base case and fix the estimated coefficient for that base case at 0 while we estimate the others. So that's kind of a really common approach. And you'll see that here with HMMs if you apply covariates to those transition elements. Okay, so we don't really need we can just kind of gloss over this, but I think it's important to know that we kind of wrote our data or the latent process as this vector x that's subscripted from 1 to capital T. And then on top of that, we have our observations, which are our raw data. In the simplest case, this will be a univariate vector, which we'll start here using we'll use y sub I, where I again will be the length of the time series from 1 to capital N, and N here might be the same as T. So the states here again are going to be this latent or discrete process that we don't directly observe, and then again we have these transition probabilities. So this matrix has to be estimated. It represents the probability of transitioning between these different discrete states in the Markov chain. And then what we can get out of that are what are known in the HMM literature as emission probabilities. So these are representing how likely each of the states are at any particular time step in our time series. And so for each, think about it this way, I guess for every different time step, we could summarize how likely we are in state 1 or state 2, for example, for a two-state model. And that's represented by this theta, where theta is subscripted from I to n, where n is the number of, kind of the dimension of the HMM. So one thing we might be interested in getting out of HMMs also is what is known as the marginal distribution, which is kind of the probability of our data. But to do that, one of the things here is that we need this. What the model really gives us is what's known as the conditional distribution, which is the probability of being in our probability of observing the data, this y sub t, given that we're in each of the states, but we're probably more interested in what the probability of the data is itself. So to do that, there's some summations which we can use to marginalize over all of the different states of nature. And again, this delta represents the stationary distribution, which we talked about a few slides ago. That can be calculated by exponentiating the matrix of transition probabilities, the gamma, from that HMM. Estimation, in general for HMMs can be quite complicated because we're dealing with kind of this joint likelihood of our observed data, the probability of or likelihood of y sub t given our latent state or latent process, the x sub t, as well as the kind of the likelihood of this underlying transition between states, which is the probability of x sub t, probability of being in x sub t given x sub t minus 1. As I said, estimation for this, given this kind of this joint likelihood, estimation is generally done in a maximum likelihood setting. There's a few different ways to approach this, and conventionally what's been used is what's known as a forward-backward algorithm, and so this is where the forward-backward algorithm is used to calculate the probability of an observed data sequence, which are y sub t's. The second algorithm is the Viterbi algorithm, and this is used to generate the most likely states, which is also really useful. So this is kind of our the most likely states as we go through the time series. And then the expectation maximization or EM algorithm, which is also used in Mars. But this algorithm within an HMM can be used to estimate and update our parameters. And so generally what's done is we apply the forward-backward algorithm, then we apply the Viterbi algorithm in this using the EM algorithm to basically do that. So we can then take our likelihood here, which is the probability of being in a state given our state at time t, given our entire observed data sequence, and factor that into over here the probability of being in that state sequence, being in that state given the data up to that state, times the likelihood of all of the future data given where we are now, given the state x sub t where we are now. So that's just one way to kind of factor the problem to make the estimation a little bit simpler. But in general, this is quite complicated, done in a maximum likelihood setting, and there are approaches for dealing with this in a Bayesian setting that we can talk about if you're interested, but kind of beyond the scope of this. So the forward-backward algorithm, the last slide we just talked about this briefly, but basically there's 3 steps here, and sometimes we combine step 2 and 3. The first step is to estimate the forward probabilities, and so this is estimating the probability of being in state x sub t given all of our data up to the current time step, which is little t. Then the second is to estimate the backward probabilities, and so given where we are now, or the state of nature x sub t, what's the probability of the future sequence of data from this point forward, which is the y that's subscripted from little t plus 1 to capital T. Then there's a smoothing step, and so this smoothing step is important because then we calculate the marginal likelihood of the sequence of the state variables x sub t given our data y. Okay, so the theory behind HMMs is there's a lot of literature out there. As I said before, the 2 books by Zucchini et al. The first and second editions of those books are quite useful for really diving into that. So I think that will be a good reference for reading material for this class if you want to use HMMs for your class project. But I think we'll kind of leave it there and then start talking about some transitions to dealing with some applications of HMMs to the kinds of data that we're interested in working with for this class. So as the first example, I wanted to just kind of explore a simple 2-state model of rainfall in Seattle in just this last winter, which has been pretty kind of gone through oscillating between some really dry spells and then again some pretty big storms. So I accessed this data from Weather Underground, and it's stored in a CSV file within the GitHub repo. And this is just a kind of a plot of what the data or the time series looks like. This is daily rainfall data going back to November 1st, which I've indexed with day 1. And then we have precipitation measured daily, measured in inches for the next about the next 3 months. So one way to deal with this type of data is that we could model that rainfall directly, and so we could just take that data from the previous slide. We could fit a Mars model to that. The downside potentially to doing that is that we've got quite a few days with no rainfall, so we've got this zeros problem, which makes things a little bit messy. We could also, another way to do that would be to fit a time series model and then impose some other distribution on top of, instead of assuming that the data were normally distributed, we could assume that things were a mixture. So we could fit like a delta glim type model where we had a model for whether or not it rained, and then a second model for modeling the amount of rain given that it did rain. A third approach would be to take kind of a time series model and impose a more flexible distribution on top of it. So something like a Tweedy distribution, which can capture both the positive values that are skewed as well as zeros. For the case of illustrating an application of HMMs, what I did here is just took the data and then I categorized it whether or not rain occurred, and we'll fit an HMM to this data. So the output here is not going to be the amount of rainfall. It'll be classified as 0 or 1 depending on whether or not rain occurred. Okay, so questions we might be interested in from this type of application are, we can certainly focus on conditional probabilities. What's the probability of it raining tomorrow given that it's raining today, or kind of related? What's the probability of it raining tomorrow given that it's not raining today? And those are things we would get out of the same transition, or the same matrix of transition probabilities that we estimate. We might also be interested in questions related to persistence. So a good example would be, on average, how many days might we expect in the future to go without observing rain? And those are all things that we can get out of HMMs pretty easily. This type of this is a pretty simple example. I think that for the purposes of this example, we don't really need HMMs to address these questions. They'd be overkill, and the reason for that is that daily rainfall is really not measured with any uncertainty. There's multiple weather stations in Seattle that are measuring rainfall. There's probably a very small CV of error associated with it, so we could assume that there's no error. But for the sake of this application, that makes the problem not not that challenging. So I think we could also take our data, and given that we know our kind of state of nature, whether or not it rained, we can also pretty easily calculate the elements of these transition probabilities directly. So we can calculate the probability that it rained, at time step t+1, given that it rained at time t, by just taking the total number of consecutive rainy days divided by the total number of rainy days. And so for this case, we can create this difference variable to indicate no change, and then just calculate this in one line of our code, which gives us the probability of it rained at time t+1, given that it rained at time t. But I think for most of the applications that we're dealing with in fisheries and ecology, we actually have zeros, and so we have to have some kind of measurement or observation error. So let's just take basically the same approach. We'll assume that the rain gauge data has a tiny amount of observation error, and we'll fit an HMM to that data. So for this application, we'll use the CRAN package that's called Detmix S4. If you haven't worked with S4 objects, this is probably a good intro to that. There's a vignette on the package that's on CRAN that you can refer back to that has some pretty simple examples, and this is one of the more widely used packages. Okay, so to use this Detmix S4 package, there's two kind of core functions that we need to get a little bit familiar with. The first is that there's this function Detmix, and so the Detmix function uses the kind of the formula syntax that we've used for fitting LMs and GLMs and ARIMA type models in this class. we have to specify a couple of these different arguments. The first is going to be, we're going to set up a formula first for modeling whether or not it rained. We use the tilde and the 1 just to indicate that there's going to be, this is basically equivalent to an intercept-only model with rained. So this whether or not it rained as a categorical response. It's got 2 levels. So we've got the number of states, which is n states, we'll set to 2. The transition matrix, here we won't include any covariates in that formula, so we'll just have tilde 1 representing the intercept-only model. Our family argument here will be binomial because that will be, we have this categorical response, 0 or 1, depending on whether or not rainfall occurred. And then the data object is this, or the data frame is this, this rain data frame that we read in previously. So this just goes through, all of these different attributes where we specify the number of states, the transition probabilities, the family. There's a wide range of families for using in Detmix S4. Just like in fitting GLMs, you can look at all of the families by looking at by querying the GLM response function. And so that first function, calling Detmix, will actually just set up the model for us, but it won't actually do any fitting. And so I think to do the fitting, we need to apply the fit function, which is also in Detmix S4. We should probably have done the Detmix S4 : notation here, but the fit mod object now will include the fitted object with parameters that's estimated using maximum likelihood. So if we look at the output of this model, we can type summary fit mod and see the estimated transition matrix, which is the probability of transitioning from state 1 to state 2. So the probability of staying in state 1, for example, is about 77%. The probability of staying in state 2 is about 59%. So right off the bat, one of the warnings or things that I wanted to flag for everybody's attention is that if we look at the values of this transition matrix and just change the seed, we can see that we get very different estimates depending on this value. So going back to the previous slide, our seed was 1, 2, 3. The probability of transitioning from 1 to 1 was 0.77 and 0.59 for state 2 to state 2. If we just change the seed, that 0.77 changes to 0.59, and state 2 here, I guess these essentially are basically swapping. So we get very different answers or interpretations of what those states represent. And as you start playing with the seed, you can start getting estimates that diverge from these kind of 2 solutions, and so you can get kind of a wide range of solutions depending on what these values of this seed are. The seed issue is kind of a known problem with HMMs. It becomes more of an issue as you start adding more than 2 states. And there's some pretty easy ways to deal with this, which are especially things that you want to consider as you start using HMMs for your real work or writing up papers, etc. So the first obvious step is to change the control parameters, and so we talked about this briefly when we used the Mars package and set the control criteria for identifying convergence in the EM algorithm. We can do the same thing with the Detmix package, and unfortunately for this particular application, we can crank up our number of maximum iterations or decrease our tolerance significantly, but it won't actually change the outcome. We still get kind of a wide range of solutions. So a second option, which I think is it's pretty robust. It's not the most efficient, but we can start the model from a large number of different starting values, and then record the best fit across all of the models that run to convergence. And so in this case, this is just some pseudocode for illustrating how you'd actually do this. We iterate through this loop a large number of times, preferably more than 100. We fit the model repeatedly by using the fit call. And then if the AIC value of our fit mod object is better than what's ever been observed before, then we save the best model and we reset our best ever observed value of AIC. You don't have to use AIC. You could use any other criterion you wanted, but this would just kind of loop through and identify what's really the best solution possible across these 100 different iterations. Okay, so let's move on to a slightly more complicated example here. So I wanted to start again with using some real data. This is data pulled from the Cal Coffee ichthyoplankton cruises in Southern California. Represents some data that I've been working on with Mary Hunziker and other collaborators. And there have been some recent papers using this long time series going back to the late 1950s to identify cool versus warm regimes. And so you can think about, there have been big fluctuations in species like anchovy and sardine. There's been also some of these lanternfishes and smooth tongue that have been used to identify warm versus cool regimes. And so in the case, for this first example, we'll focus on the California smooth tongue, which is one of the species here. And we can look at kind of the average catch per unit effort for this species. And we can see that things are pretty variable. There's also been some extremely abundant years of the species and years where the species is basically not present. So one of the things to keep in mind is that this survey is it's kind of a spatially gridded survey. The effort will change year to year. And so we have potentially spatially changing effort, spatially changing distribution. So if you were going to apply this in real life, you would want to do some index standardization to account for that shifting effort, and then quantify the shifting spatial distribution on top of that. For simplicity here, though, what we'll do is just take the mean abundance in the Cal Coffee survey across all stations from the April to May period, representing kind of the spring months. And that's what this mean catch per unit effort looks like for California smooth tongue. Okay, so we'll start by fitting just a simple two-state model using the Detmix package. The assumptions here will be that the data will be log transformed to make it approximately normal. We could also not do this transformation, but adopt a different family. By default, the default family in the Detmix package is Gaussian, so we're not specifying that. We're modeling the log of catch per unit effort is just a function of the intercept, two states, and then we're just going to simply fit the model using the fit call. Okay, so the first thing we want to do is look at how to get predictions out of the Detmix fitted object. The first thing we want to maybe get out are the estimated state probabilities, and so we could work with either of two different things. And it's important to remember which of these is of most interest for your application. So the first thing is, what's the most probable state trajectory? And so this is essentially what sequence of the underlying states is most probable given our data. Or what's the most probable path through the data given our observed, what's the most probable path or sequence of states given our observed data? This comes out using the Viterbi function in the Detmix package, which obviously applies the Viterbi algorithm. The second is to look at calculating what's the marginals, or what's the probability of being in each state at each time step. And that's something that we get out using the posterior function. And so these two outputs are going to be very similar, but it's important to remember that there's this important distinction between which of these state trajectories is most probable versus getting out the actual marginals at each time step. So the most probable states are we're gonna focus on that. I think that's been more often useful for the applications that I work on. So to get the the most probable states. We apply the posterior function to our fit mod fitted object, and then for each of those, we're just going to take the maximum state and plot what that looks like over time. So we kind of alternate between these two states representing maybe a cool and a warm period. Okay, so the Detmix package doesn't have a predict or forecast function like we've seen with some of the functions like ARIMA or the forecast library. And so I think that even though it doesn't include those, estimating data and generating future predictions is pretty straightforward. We can get the means out of the model using our summary function, and this gives us the coefficients representing the mean catch per unit effort for each of those two states. And then we can look at what the predictions look like on top of our raw data. So again, this is going to be more choppy and less smooth than what you would get if you fit, say, a univariate state-space model of the same data, because the HMM is clearly not capturing some of these changes that are not discrete. So that the HMM will be advantageous when we're kind of alternating between cool and warm regimes. For any of these trends that are maybe non-stationary and more linear or gradual, the HMM will do probably a worse job of that. But you can see that it's definitely picking out some of these years that are where we're getting low catch per unit effort. The HMM is doing a really good job classifying those as a different regime from this kind of higher period where we get higher catch rates. Okay, so if we took the estimated values and states from the last slide, and we wanted to apply some diagnostics, you would do the same kinds of diagnostics that we did for using, say, the Mars package, where we could have residuals on the observation model or the process model. If we applied those diagnostics, going back to our last slide, on something like this trend, the autocorrelation wouldn't look great because this model doesn't really capture that process very well for the end of the time series. So one solution, I guess, to dealing with this autocorrelation issue or the lack of good diagnostics would be to consider alternative models with more numbers of states than 2. In this case, we can do some model comparison to look at which of the two models would be better, whether it would be advantageous to fit a 3-state model. And so starting with our 2-state model, the AIC value coming out of that would be about 119. We can just repeat our same model call using 3 states instead of 2, and here we would get 122, which is a higher value of AIC, indicating a less parsimonious model compared to the 2-state model. So adding a state here doesn't really seem to improve things. We could probably, just to be on the safe side, implement this within a similar loop where we would start each of these models from 100 different starting values and ensure that the best values across all of these are still different. That's probably the case, but it would be good to just verify. One of the advantages to working with HMMs is that we've seen in a multivariate time series setting using Mars models or something like DFA, we can take a large number of time series and apply something like DFA as a dimension reduction tool to identify a smaller number of latent processes or trends representing or characterizing kind of the behavior of the set of time series in the multivariate setting. So HMMs can be thought of as a really similar case. I think that in contrast to DFA, where the underlying process is this continuous process, the underlying process in a HMM is going to be a discrete transition between discrete states, and so it's going to be used to answer slightly different questions. But we can do this in a multivariate setting, and so I think that like DFA, the assumption behind a HMM is going to be that the underlying process is going to be the same for all time series, although the time series might differ individually with respect to their lengths and their error distributions. So in a DFA, I guess we were estimating loadings for each of the time series on each of the trends. In the HMM, we're not going to do that. We're going to assume that each of the underlying state processes is representative of all of the time series that are being fed into the model. Okay, so in the Detmix function, we basically do this in a multivariate setting by changing all of our arguments to lists, which are going to be input. And in using the same kind of CalCoffee data, I'm just going to add a second species for now, which is going to be pretty correlated with the first, the California smooth tongue, and we'll analyze simultaneously the underlying or fit a HMM to each of to both of these species combined. Okay, so here's how we fit a two-state model with two species as responses. So the first thing we need to do is just kind of reshape our data, which we'll do using the Reshape 2 library. And so the data frame that we get out of this just represents, it's the rows are the number of years. The columns here are going to be the year variable, and then the two species that we're modeling. And this is again we'll be working with this in log space to assume that everything is normally distributed. Okay, so here's how we work with those list objects. So our formula here will be a list of formulas where each species is assumed to be modeled with an intercept only. Again, you could have covariates here. The covariates could be specific to each species or different. We'll assume again that our model is only going to have two states, which was supported using the univariate case. Our family object here will be now a list, and so you can have a different family for each of the different input variables that you're including in your response list. Each of these is going to be assumed to be Gaussian because we've log transformed the raw catch per unit effort. So again, we'll just the call should look very similar to what we did before with the univariate setting, with the exception of adding these two lists. And again, we can use the same fit call to actually fit the model and estimate the parameters. Okay, so we could also have situations where the time series are of different length. For example, if one time series was missing the first half of the values, there's an n times argument in the Detmix package that becomes pretty useful for actually letting your time series have different lengths, or maybe you have different samples for different surveys. So I'm not going to illustrate an application, but just know that that's there and is pretty useful for incorporating multiple different kinds of data. Okay, so before we move on to lab, just to summarize, HMMs are a pretty useful approach for identifying latent state vectors where the latent states are these discrete classes, and at the same time we can estimate the discrete transitions between these different classes. In a HMM setting, in the applications that we're working with for this class, many of the applications, especially those in R, are done with maximum likelihood methods. These are really fast, but occasionally, as we've illustrated, the algorithms can get stuck or they can depend on initial starting values. The workaround for this is to work with multiple starting values and initialize the estimation from a large number of different starting spots. Bayesian estimation is becoming more popular for these methods. It's generally beyond the scope of this class, but I think it's fairly straightforward to build these models using bugs or JAGs, and a little bit more complicated in some of the newer software tools like TMB or STAN, in part just because these models are trying to rely on the gradient of parameters with respect to the likelihood, and it's really hard to do that or impossible with a discrete parameter. So if any of you have any questions or want to use these models for your class projects, certainly talk to us, but that's just a quick overview of HMMs and time series. Thanks.